Welcome to the exam wrapper for test 1. I'm doing problem number 2, which is on it's the spring problem, so I'll read the problem. A block of mass m is connected to two springs. Each spring has a relaxed length of L0. The spring on the left has stiffness Ks, and the spring on the right has stiffness 2Ks. As shown in the diagram, the block is initially released from rest at x equals L0 divided by 3. The bottom surface supporting the block is frictionless. So, as we do in part A, it's always a good idea to list all the objects that are interacting with our system. And in this case, our system we take to be the block. So we have the Earth and the surface, but since we're saying those forces, although they are negated and equal 0. And then the other forces that we are considering are the forces provided by the spring on the left and the spring on the right. So in part B, we are calculating the net force and expressing it as a vector. So we have the spring force equation, which says that F net is equal to negative Ks times L0 minus L. And all we're doing in part B is just applying that twice, first to the spring on the left, then to the spring on the right. So for the spring on the left, we get negative Ks is times 4/3 L0 minus L0. And the reason we say 4/3 L0 is because we're saying L is at position 4/3 times L0 as stated in the problem. And the force provided by the left spring comes out to be negative 1/3 Ks L0. The force provided by the spring on the right we write as negative 2Ks 2/3 L0 minus L0. And again, we get that same L minus L0 where L is equal to 2/3 L0. And so then we can subtract 2/3 L0 minus L. And also, it's 2Ks this time, and we're also negating it since the force is going on the opposite direction. So we can sum the forces in the x direction, and in the end we get negative Ks L0 as our total F net in the x direction. Moving on to part C. In this case, we're calculating the velocity based on our previous F net calculation. And here we can just use Newton's second law. Very simple formula. V final is equal to V initial plus F net over m times delta t. And we just plug in our F net in the x direction, and we get the final velocity. Since the initial velocity is equal to 0, since we're releasing it from rest, we get final velocity is equal to negative Ks L0 over m times delta t. In part D, we're calculating the new position. And the initial position is given to us as L0 over 3 in the x equals L0 over 3. And we can use the derivative of of Newton's second law. R final is equal to R initial plus V average delta t. In this case, a good approximation for V average, since F net is changing over time in the x direction, is that V average is approximately equal to V final, which we know to be negative Ks over m L0 delta t. Then we can plug in for R initial that we know L0 over 3 and V average, or V final in this case, negative Ks over m L0 delta t, and that gives us L0 over 3 minus Ks m L0 delta t squared in the x direction as our final position. In the final part of the in the final part of the question, we come full circle back to finding the F net, the new net force on our object. So again, we're using that same spring force equation, negative Ks L minus L0, and we plug back in what we calculated as the new net force, and doing it exactly the same way as we did in part A, part B, we sum the forces, and we get the net force to equal negative Ks L0 plus 3Ks squared m delta t squared. And we get that squared Ks when we expand out, when we multiply those Ks's through. That's where that comes from. So that's really the summary of question number 2. Thank you for watching. I'm signing off.